Welcome back to my channel. As language models continue to scale, researchers are exploring techniques to target only the most relevant parameters in order to reduce computational costs. Today, we're diving into low-rank adaptation, a method that fine-tunes a model by updating only a small subset of parameters. Let's get started. Fine-tuning enables LLMs to gain domain-specific knowledge, but fine-tuning large models is prohibitively expensive. To address this challenge, researchers have explored different techniques. Adapter layers add only a small number of extra parameters, but their sequential processing significantly increases inference latency. Directly optimizing prompts is challenging, limiting its effectiveness compared to other methods. LoRA addresses this challenge by freezing pre-trained weights and injecting trainable, low-dimensional update matrices into each transformer layer, reducing the number of trainable parameters by up to 10,000 times while achieving on-par or better performance without latency. Instead of updating all the pre-trained weights, LoRA keeps them frozen and learns a much smaller, low-rank update. The delta W is further decomposed into two smaller matrices B and A, where the intrinsic rank of B and A is far less than the dimension of the original pre-trained weight matrix. Take GPT-3-175B as an example. This large language model has 96 layers, each with an input and output dimension of 12,288. If LoRA is applied to just one attention weight matrix per layer, the number of trainable parameters is calculated as 2 times the number of layers times the layer dimension times the rank. The factor of 2 accounts for the two low-rank matrices A and B. When rank equals 8, trainable parameters amounts to 18 million, which is about 10,000 times fewer than GPT-3's total number of parameters. To stabilize training, LoRA initiates A with normal distribution and 0 for B, so BA is 0 at the beginning of training. B and A are then updated through backpropagation during fine-tuning. Because the pre-trained weights and BA share the same shape, it's easy to attach or detach BA without modifying the original weights. This allows us to maintain different BA modules for different downstream tasks. When switching between tasks, we simply subtract the current BA and add a new BA to the original weights without introducing any additional inference latency. LoRA can be applied to any weight matrices, but this study focuses on adapting only the attention weights for simplicity. LoRA is evaluated across different LLMs including Roberta, Deberta, GPT-2, and GPT-3-175B. These LLMs are tuned by 6 different approaches. With Roberta Base, Roberta Large, and Deberta XXL, LoRA performs on par or better than other adaptation methods. With GPT-2 Medium and Large, LoRA outperforms all baselines with comparable or fewer trainable parameters. As a final stress test for LoRA, LoRA is evaluated on GPT-3 with 175 billion parameters. LoRA matches or exceeds baselines on all 3 datasets. With only 4.7 million parameters, LoRA performs nearly as well as LoRA with 37.7 million parameters. To further explain the properties of the low-rank adaptation, the research team performed a sequence of empirical studies. To determine which subset of weight matrices should we adapt, the research team did the following experiment. With a parameter budget of 18 million, which corresponds to a rank of 4 for GPT-3-175B if we adapt 2 types of attention weights, the model performs the best if we adapt both Q and V weight matrices. Performance significantly drops if we adapt Q and K instead. To determine the optimal rank, the research team found out that a rank as small as 1 suffices for adapting both WQ and WV on WikiSQL and multi-NLI, while training WQ alone needs a larger R. This suggests the update matrix delta W could have a very small intrinsic rank. To find out the connection between delta W and W, the research team projects W onto a subspace spanned by the top singular vectors of delta W and takes the Frobenius norm of this projection. U and V are the left and right singular vectors from delta WQ, WQ itself, or a random matrix. The Frobenius norm measures how much weight is captured in this projected subspace. When R is 4, and using the U and V from delta WQ, the Frobenius norm is 0.32. When using U and V from a random matrix, the Frobenius norm is 0.02. Since 0.32 is much greater than 0.02, it suggests that the subspace spanned by delta WQ has significant correlation with WQ. The experiment shows the same conclusion when R is 64. This analysis suggests that LoRa's low-rank updates help enhance useful features that the pre-trained model knows about but doesn't emphasize enough for specific tasks. Essentially, LoRa magnifies latent features of the base model to make it better for new tasks without retraining the entire network. Fine-tuning large language models demands lots of computation. LoRa offers an efficient adaptation strategy that maintains high quality without adding inference latency or reducing input sequence length. It also makes task switching fast and easy. Future work includes combining LoRa with other adaptation methods, exploring how fine-tuning transforms pre-trained features, developing more principled methods to select weight matrices to adapt, and investigating the implications of rank deficiency in weight updates and potentially in the pre-trained weights themselves. If you found this video inspiring like we did, don't forget to give it a thumbs up and subscribe to the channel. Thanks for watching, and we will see you in the next video.